Sometimes your lungs are just so sick and tired of breathing that they just want to give up. At that point, you comfort them and you show them some love by eating a big old bowl of fat.
Ketogenic diet has neurological benefits. Why do we have to eat such an enormous amount of food?
Complex science, clear explanations. Class is starting now. Hi, I'm Dr. Chris Masterjohn of chrismasterjohnphd.com, and you're watching Masterclass with Masterjohn, where we are now in our 12th in a series of lessons on the system of energy metabolism. And today we're talking about how fat and carbohydrate generate different amounts of carbon dioxide, and why that has important implications to how we would manipulate the fat versus carbohydrate content of the diet in different situations. Now, we're going to start talking about the differences between fat and carbohydrate before we talk about protein. And that's because carbohydrates and fats are relatively simple in the different variations of those molecules, whereas protein metabolism is really complex. So we're going to deal with carbs versus fat first, then we'll move on to talking about where protein fits into this mix in later lessons. When we looked at the citric acid cycle, we saw that we didn't have enough atomic oxygen to release the carbons in the acetyl group as carbon dioxide. We made up for that by taking oxygen atoms from water. We needed 3 oxygen atoms, and so we took them from 3 water molecules. 2 of the water molecules were used directly, and 1 was used indirectly, bringing the oxygen atom to the citric acid cycle in the form of phosphate. We're going to see the same principle that we make up for needed oxygen by incorporating water, and that's the limiting factor for releasing carbon dioxide when we look at carbohydrate versus fat. Shown on the screen is glucose as a representative of carbohydrate and palmitic acid as a representative of fat. If you look at the glucose molecule, its chemical formula is C6H12O6. A carbohydrate is a hydrated carbon, carbons that have water incorporated. The chemical formula of water is H2O. Carbohydrates generally conform to a hydrogen to oxygen ratio that reflects that. And you can see that the ratio in glucose is H12O6. That's a 2-to-1 ratio of hydrogen to oxygen. Not every carbohydrate is exactly this ratio, but glucose is, and in general, carbohydrates at least approximate that ratio. A fatty acid is a carboxylic acid that's soluble in fats and oils. And palmitic acid is an example of that. Palmitic acid is a 16-carbon fatty acid, and if you count the carbons, you'd start 1, 2, 3, 4, and work your way up to the 16th carbon, which is part of a carboxyl group. Carboxyl groups make something a carboxylic acid, and so fatty acids are specific forms of carboxylic acids that are soluble in fat instead of water. If you look at either of these molecules and you compare them to the chemical formula of CO2, we don't have enough oxygen to release the carbon atoms as CO2. For example, in glucose, we have a ratio of CO, a 1-to-1 ratio, instead of a 1-to-2 ratio in CO2. In palmitic acid, we have C16O2. That's an 8-to-1 ratio instead of a 1-to-2 ratio. In glucose, we don't have enough oxygen to release the carbons as CO2. In palmitic acid, we don't have anywhere near enough oxygen to release the carbons as CO2. When thinking of the biochemical pathways involved, however, it's better to think of glucose and palmitic acid with respect to the carbon to oxygen ratio found in the acetyl group, because before the carbons are fully released as CO2, both carbohydrates and fats are metabolized to acetyl-CoA, and that's how they enter the citric acid cycle. If we look at the carbon to oxygen ratio of the acetyl group of acetyl-CoA, we see that it's a 2-to-1 ratio, 2 carbons for every oxygen. That's the exact inverse of CO2, where we have 1 carbon atom for every 2 oxygens. When we look at it that way, glucose has 1-to-1 CO versus the acetyl group 2-to-1 C2O. That means that glucose has twice as many oxygens as it needs to generate acetyl groups. By contrast, we can look at fat, which has C16O2, or an 8-to-1 ratio of C8O. If palmitic acid has an 8-to-1 ratio instead of a 2-to-1 ratio, then palmitic acid has only a quarter as many oxygen atoms as it needs. We're going to make up for this difference by releasing more CO2 when we metabolize carbohydrate and also releasing some water, whereas for fatty acids, we're going to require a greater amount of water in their utilization, and we're not going to release as much CO2. When you look at the fatty acid, it's important to note that you could have 1 oxygen atom or you could have 2, depending on whether you think of utilizing the fatty acyl-CoA that will result from dehydration synthesis when we join palmitic acid to CoA, or you think of the fatty acid molecule on the whole, which has 2 oxygen atoms. We can account for it in either way, but keep in mind this. If we have to release 16 carbons as acetyl-CoA, we're going to release those 16 carbons as 8 acetyl-CoA, because each acetyl group has 2 carbons. Each acetyl group has 1 oxygen atom. That means that we're going to need 8 oxygen atoms to make 8 acetyl-CoA. If we're thinking about the fatty acid, then we already have 2 oxygen atoms and we need 6 more. If we're thinking about the acyl-CoA, where we chop off the OH group during dehydration synthesis to join it to CoA, then we only have 1 oxygen atom and we're going to need 7 more to get the 8 we need to make 8 acetyl-CoA. Shown on the screen on the top line is the joining of palmitic acid to coenzyme A to produce palmitoyl-CoA. Whenever we join an acid to coenzyme A to produce an acyl-CoA, we do it by dehydration synthesis, releasing a water molecule, which is shown in purple on the right. On the second line, we see the overall stoichiometry of beta oxidation, which is the principal means by which we oxidize fatty acids to acetyl-CoA. In beta oxidation, what we're doing is we're chopping off 2 carbon units to produce acetyl-CoA. If we're going to take something with 16 carbons and break it apart into 8 pieces, we only need to cut it 7 times, because the 7th time we cut off a 2 carbon unit and the stub that's left over is the 8th 2 carbon unit. So what we see represented is that every time we cut off a new acetyl group, we need to oxidize it, and we need to join it to CoA, and we need to hydrate it to produce the oxygen atom of that acetyl group. We see that reflected that we oxidize it with FAD and NAD+, producing FADH2 and NADH plus H+. And we join the acetyl group to coenzyme A, and we use the water. So if we're going to do that 7 times, we overall take 1 palmitoyl-CoA, we use 7 FAD, 7 NAD+, 7 CoA, and 7 water to make 8 acetyl-CoA. Remember, we already have CoA, and we already have 1 oxygen atom at the end of the fatty acid. So we have 8 acetyl-CoA, and then the 7 FADH2, the 7 NADH, and the 7 hydrogen ions that were used during each slice of the 2-carbon unit. So what we see here is that if we're thinking about palmitoyl-CoA as the starting point, we use 7 water molecules to supply the 7 oxygen atoms that we need. But if we think of palmitic acid as the starting point, then we're only net using 6 waters because we're actually generating a water during dehydration synthesis and consuming 7, which is a net consumption of 6 waters. No matter how you look at it, it corresponds to the number of oxygen atoms that you would need to add to the molecule to make sure that you have 1 oxygen for every 2 carbons in the acetyl group of acetyl-CoA. Notice during the stoichiometry of beta oxidation that at no point do we ever generate any CO2. Contrast beta oxidation with the metabolism of glucose to acetyl-CoA. The net stoichiometry of glycolysis is shown on the top line. 1 glucose molecule plus 2 ADP, 2 phosphate, and 2 NAD+ make 2 pyruvate, 2 ATP, 2 NADH, 2 H+, and 2 water. These 2 water do not reflect the removal of the extra oxygen of glucose. Rather, they reflect the 2 dehydration synthesis reactions required to join 2 ADP to 2 phosphate to make 2 ATP. Nevertheless, the fact that beta oxidation consumes water and glycolysis does not consume any water reflects the fact that glucose is rich enough in oxygen that at this stage its metabolism does not require the consumption of water. In fact, it's so rich in oxygen that, as we noted before, we need to remove that oxygen as carbon dioxide. Now, glucose will get metabolized to 2 pyruvate, and each pyruvate will be metabolized to 1 acetyl-CoA. So 1 glucose makes in net 2 acetyl-CoA. If you think about the numbers of carbons and oxygens, 1 glucose molecule has 6 carbons and 6 oxygens. 1 acetyl group has 2 carbons and 1 oxygen. When we go from glucose to 2 acetyl-CoA, we're going from 6 carbons and 6 oxygen to 4 carbons and 2 oxygen. That means we need to remove 2 carbons and 4 oxygen. That's the exact number of carbons and oxygens that we would find in 2 molecules of carbon dioxide. And those 2 molecules of carbon dioxide are removed during the decarboxylation of 2 pyruvate to 2 acetyl-CoA. The decarboxylation of pyruvate has a net stoichiometry as shown on the bottom. Pyruvate plus CoA plus NAD+ makes acetyl-CoA plus CO2 plus NADH plus H+. That decarboxylation of pyruvate is the one case where we release carbon dioxide from glucose outside of the citric acid cycle. And that one decarboxylation step and 1 carbon dioxide generated for each acetyl group that enters the citric acid cycle is the difference in carbon dioxide production between carbohydrate on the one hand and fat on the other hand, which does not involve an analogous decarboxylation step. Let's look at a biochemical level how these principles are integrated. Glycolysis occurs in the cytosol and generates pyruvate. During glycolysis, we generate 2 pyruvate, which means that for every 1 pyruvate, we release 1 molecule of water. So half a cycle of glycolysis generates the pyruvate and the water. Each pyruvate enters the mitochondrion where it's decarboxylated. During the decarboxylation of pyruvate, we release one carbon dioxide molecule. The decarboxylation of pyruvate yields acetyl-CoA. Alternatively, we could have gotten that acetyl-CoA from the beta oxidation of fatty acids. The beta oxidation of fatty acids takes place in the mitochondrion and it generates acetyl-CoA directly. For every acetyl-CoA that's generated, we consume one molecule of water. Now the acetyl-CoA molecule enters the citric acid cycle at which everything else is identical between fat and carbohydrate. For every acetyl group that enters the citric acid cycle to be used for energy, we release 2 carbon dioxide and we consume 3 waters. Remember that even though the standard stoichiometry of the citric acid cycle only shows 2 waters being consumed, there's a third water that's irreversibly consumed outside the citric acid cycle to generate the phosphate that provides the oxygen atom to the citric acid cycle. So in net, when we integrate metabolism, we're still seeing 3 waters consumed. So overall, for every acetyl group that enters the citric acid cycle, we have 3 waters consumed and 1 water released for carbohydrate. That's a net consumption of 2 waters. By contrast, for every acetyl group that enters the citric acid cycle when we're burning fat for energy, we consume 1 water during beta oxidation and 3 waters in the citric acid cycle. That's 4 net waters consumed for fat metabolism versus 2 net waters consumed for carbohydrate metabolism. Therefore, fat demands twice as much water as carbohydrate during the production of energy. Before reading too much into this, we should remember that outside of breaking down carbons to CO2 in the electron transport chain, we take oxygen from the air we breathe and we turn it into water. So we shouldn't be saying that their metabolism net consumes water. It actually generates water later. But simply to release the carbons as CO2, net consumes water, and that consumption of water is twice as much for fat as for carbohydrate. If we look at CO2, if we're taking the acetyl group from carbohydrate, for every acetyl group that enters the citric acid cycle, we generate 1 CO2 during the decarboxylation of pyruvate and 2 CO2 during the citric acid cycle. That's a net production of 3 carbon dioxide for every acetyl group that enters the citric acid cycle from carbohydrate. By contrast, beta oxidation of fatty acids does not produce CO2. The acetyl-CoA enters the citric acid cycle and produces 2 carbon dioxide. So carbohydrate produces 3 carbon dioxide, fat produces 2 carbon dioxide. Therefore, carbohydrate produces 50% more carbon dioxide than fat. One of the ways that this is important is how it impacts the breathing rate. And in order to consider that, we first should review the carbon dioxide buffer system in the blood. This would normally be taught in its full detail in a physiology class, but here we'll see that it intersects in important ways with energy metabolism. Carbon dioxide in the blood will join to water to produce carbonic acid. You can add up these atoms and you'll see they all balance out. We have CO2 plus H2O makes H2, H2. CO2 plus O is CO3. Carbonic acid is an acid. In water, it dissociates a hydrogen ion, in other words, a proton, and what's left over is bicarbonate ion, HCO3-. Because carbon dioxide is acidic, we can control the acidity of our blood with our breathing rate. If we have more carbon dioxide in the blood, we'll get more carbonic acid. Because remember that the forward reaction is going to be proportional to the concentration of the substrates. These are reversible reactions, but let's consider the forward reaction first. If we have more CO2, we get more carbonic acid, and we get more hydrogen ions, which means the blood pH goes down because we have greater acidity. The nervous system responds not to the CO2, but to the acidity of the blood. As blood pH drops, the nervous system causes our lungs to increase their breathing rate. That leads to more exhalation of carbon dioxide. Carbon dioxide goes down, and that makes blood pH go up. In sum, we can say that the protons exert a negative feedback loop on the carbon dioxide production. Now, the reason that this is considered a buffer system is because these reactions are fully reversible. If we have more hydrogen ions from a different source, let's say we have lactic acid in the blood, or we have ketones in the blood that are acidic, the extra hydrogen ions from that different source will combine with bicarbonate in the blood to produce carbonic acid. More carbonic acid will make more water and more CO2, and the CO2 can capture those hydrogen ions. So because it works both ways, because more CO2 makes more acid and we get rid of the CO2 versus more acid captures the hydrogen ions and goes backwards, it acts as a buffer system to make sure that no matter where the hydrogen ions are coming from, they're never building up too much and the blood pH is never getting too out of balance. But the reason that we're interested in it here is not so much because of the buffer system, but because carbon dioxide production is affected by our metabolism. And that in turn influences the breathing rate. So if we're eating more carbohydrate, we're going to get more CO2. We're going to get more acidity in the blood, and we're going to increase our breathing rate to get rid of the CO2. Now, the CO2 on a high carbohydrate diet shouldn't go all the way back to normal, and that's because there are other mechanisms of compensation. So controlling the breathing rate is called respiratory compensation. But there's also renal compensation, where more acid makes the kidneys just excrete the acids, and that reduces the burden on blood pH. So more CO2 will produce more respiratory compensation and more renal compensation. The net result is that respiratory compensation makes CO2 go part of the way back to normal, but renal compensation allows some of that CO2 to remain in the blood. So we would expect high carbohydrate diets to make you breathe more rapidly and to leave the blood carbon dioxide level higher than it would otherwise be on a lower carbohydrate diet. One of the reasons that this is important is consider the case of someone who has injured lungs. The lungs are injured to such an extent that that person has to be on artificial ventilation in the hospital. If that person needs to be connected to a machine to allow them to breathe, then clearly you don't want them breathing more than they have to. So to reduce the stress on the lungs, you would reduce the carbon dioxide generated during metabolism. If the lungs have less to do, then they have more energy left over to heal during treatment. That means that a low carbohydrate, high fat diet may allow someone to recover faster on artificial ventilation, get off the artificial ventilation and out of the hospital faster with a greater speed of improvement and a greater likelihood of healthy survival. Shown on the screen are the results of a study where 20 adult patients requiring artificial ventilation were fed either a standard mixed diet or a low carbohydrate, high fat diet through a feeding pump. You can see the proportions of carbohydrate and fat at the top of the graph. What you see is that on the fat-rich diet shown in purple, the blood carbon dioxide level was lower than on the high-carb diet shown in green. Shown on the screen now is the same color coding scheme, green for high carbohydrate and purple for low carbohydrate. And in this case, we're looking at the breathing rate, and we're looking at it in breaths per minute and in breathing volume. Whether it's the breaths per minute or the breathing volume, we see that there was less breathing to do on the high-fat, low-carbohydrate diet. Shown on the screen is the number of hours spent on the ventilator. The individual data points are individual people, and you can see that there was a lot of variation. The line represents the mean. But you can see that people who were eating the higher carbohydrate diet spent about 50% more time on the artificial ventilator than people who were eating the high-fat, low-carbohydrate diet. So a high-fat, low-carbohydrate diet produces less CO2, reduces the need of the lungs to breathe. By reducing the stress on the lungs, you allow people on artificial ventilators to heal faster and get off the ventilation and out of the hospital faster. In a critical case, healing faster could even mean a better chance of survival. On the other hand, we don't want to just say high-fat, low-carb is good because reducing stress on the lungs is good. If your lungs are healthy, it's not bad for them to have to breathe. That's what they're supposed to do. Additionally, carbon dioxide plays important roles in many metabolic processes in the body. Shown on the screen is the role of carbon dioxide in vitamin K metabolism. The purpose of vitamin K is to take carbon dioxide and add it to glutamate within proteins. That glutamate normally has one carboxyl group which carries one negative charge. If you add carbon dioxide during the process of vitamin K-dependent carboxylation, you get a second carboxyl group on glutamate, which adds a second negative charge. That increases the ability of the protein to bind to calcium, because calcium has a +2 charge, and with vitamin K-dependent carboxylation, you've created a -2 charge on the protein. +2 is attracted to -2. Sometimes this helps calcium glue a protein into a proper three-dimensional structure. That's the role that it plays in the regulation of blood clotting. Sometimes this allows a particular protein to shuttle calcium to where it belongs and keep it out of where it doesn't belong. That's the role of preventing soft tissue calcification and mineralizing bones and teeth. In other words, you don't put calcium in your kidneys to make kidney stones, but you do put it in your bones to make strong bones, and you do put it in your teeth to make teeth that are resistant to tooth decay. This also plays an important role in growth because the same proteins that shuttle calcium into the right places also keep it out of the growth plates during the growth of long bones. When you and I were children, we were growing and growing and growing. At some point, the cartilage that was expanding to make new bone that was responsible for making us taller and taller and taller calcified, and it couldn't grow anymore. We stopped growing. You probably can't see it in the video, but I'm only 5'7½". I really like to claim that ½ inch because, man, when you're 5'7", 5'7½" makes a difference. So perhaps if I had more vitamin K in my diet and I had more vitamin K-dependent carboxylation, I would have grown a little bit taller. Maybe I could have even been a baller. Anyway, vitamin K plays an important role in growth in that way. Vitamin K also carboxylates a protein called osteocalcin so that it can bind to the calcium in bone. Its actual function is to be released from the bone during certain times to act as a hormone that improves insulin and insulin sensitivity and improves testosterone in males and even increases energy utilization during exercise. All of these functions of vitamin K depend on carbon dioxide. Now, does a standard low-carbohydrate diet produce CO2 levels that are so low that you're going to have defects in all of these processes? No one's really ever studied that. But we can point to this and say, CO2 is important, so let's not try to minimize it necessarily. In addition to supporting the roles of vitamin K, carbon dioxide also supports the roles of biotin. The difference is that whereas vitamin K uses carbon dioxide directly, biotin carboxylates proteins using bicarbonate. But as we saw before, bicarbonate is directly produced from carbon dioxide when it's dissolved in water. The other difference is that vitamin K mostly plays roles outside of energy metabolism, whereas biotin mostly plays roles in energy metabolism. So we'll look more at biotin later when we get to the points where biotin becomes important for the system of energy metabolism. In addition to this, carbon dioxide is released from skeletal muscle at a greater amount during exercise. It doesn't matter whether you're burning carbohydrate or fat, more energy expenditure means a greater rate of the citric acid cycle and greater CO2 production. When you have CO2 released from skeletal muscle, that's when skeletal muscle needs a lot of oxygen. And so CO2 released during energy metabolism acts on hemoglobin to allosterically stimulate the release of oxygen. That means greater oxygen can be delivered to the skeletal muscle where it's most needed. Now, this is part of what's called the Bohr effect, and that's Bohr, B-O-H-R, named after Christian Bohr, who discovered the basic principles. This isn't the entire Bohr effect. The Bohr effect also notes that acid releases oxygen from hemoglobin, and that carbon dioxide and hydrogen ions act synergistically. Carbon dioxide, as we saw before, can be a source of those hydrogen ions, but so could lactate, so could ketones. And particularly lactate during intense exercise is going to be an important source of local hydrogen ions to stimulate the release of oxygen. However, part of the Bohr effect is stimulated not because carbon dioxide is acidic, but because carbon dioxide directly binds to hemoglobin to allosterically regulate it to stimulate oxygen release. And in that context, you could make an argument that greater carbohydrate burning during exercise would lead to greater CO2, which would lead to greater oxygen delivery to the muscles. So once again, we don't want to take the idea that less CO2 is always better. In this case, more CO2 would probably improve athletic performance. Finally, the different amounts of CO2 produced during fat and carbohydrate are responsible for what's called the respiratory quotient, or RQ. This is especially relevant to exercise science, and it's been used in a lot of studies to look at how different types of exercise determine how much carbohydrate and how much fat you burn for energy as an acute effect of that exercise. The respiratory quotient, or RQ, is measured in a respirometer, which is going to measure the oxygen you consume and measure the CO2 you produce. The ratio of CO2 produced to oxygen consumed is called the respiratory quotient. If you look at glucose, it has a respiratory quotient of 1. If you look at palmitate, it has a respiratory quotient of 0.7. That reflects the fact that glucose releases more CO2 per unit oxygen consumed. Exactly why the RQs work out to 1.0 and 0.7 between glucose and palmitate would require greater in-depth look at these metabolic pathways, and we'll eventually get there. But we can note for now that for glucose, the oxygen is consumed in the respiratory chain, which is tied to the citric acid cycle. The decarboxylation of pyruvate is responsible for 1/3 of the carbon dioxide released from glucose, and it doesn't require oxygen. By contrast, palmitate only releases CO2 in the citric acid cycle, which is dependent on oxygen, and that's why glucose releases more CO2 per oxygen consumed. We can relate it back to what we've talked about today simply by noting that carbohydrate generates 50% more carbon dioxide than fat does, and that's going to result in a higher RQ. In later lessons, we'll be able to see exactly why they work out to the numbers that they do. So we've seen that because of their different amounts of oxygen, carbohydrates and fats generate different amounts of carbon dioxide. They also consume different amounts of net water. The different amounts of carbon dioxide are important in numerous ways. And in the case of artificial ventilation, where your goal is to reduce stress on the lungs, a high-fat, low-carbohydrate diet is very valuable. On the other hand, carbon dioxide plays important roles in supporting the actions of vitamin K and biotin, and plays an important role in the delivery of oxygen to tissues, especially during exercise. In those contexts, carbohydrate could play an important role by increasing the amount of carbon dioxide produced. We also see that this principle is used in research studies in the form of the respiratory quotient, where we can use the CO2 produced per oxygen consumed as an index of whether someone is burning more carbohydrate for their fuel or more fat. The audio of this lesson was generously enhanced and post-processed by Bob Devodian of Torian Mixing, giving you strong sound and dependable quality. You can find more of his work at torianonlinemixing.com. To continue watching these lessons, you can find them on my YouTube channel at youtube.com/chrismasterjohn, or on my Facebook page at facebook.com/chrismasterjohn. Or you can sign up for MWM Pro to get early access to content, enhanced keyword searching, self-pacing tools, downloadable audio and transcripts, a rich array of hyperlinked further reading suggestions, and a community forum for each lesson. If you really want to own these lessons, study them, and get the most out of them, you can sign up for MWM Pro at chrismasterjohnphd.com/pro. All right, I hope you found this useful. Signing off, this is Chris Masterjohn of chrismasterjohnphd.com. You've been watching Masterclass with Masterjohn, and I will see you in the next lesson.